Today we have Ken Millett, who's going to tell us about entanglement of polymers. Take it away, Ken.
Okay, thank you very much, DeWitt, and thank you everyone who's joining us. Uh, I don't know who's there, but I see pictures of people every once in a while. And I'm going to write. Here is sort of the general plan of maybe a bit of a brief discussion, a historical overview, uh, and then a focus on Eleni Panagiotou PhD work, and then applications of the ideas that I'll be talking about there about models for polymer gels and periodic boundary conditions and applications that have involved her and myself and some of our colleagues. So with that, and lest I ever forget, I should just mention or show you the names of various folks who are involved in this. Spencer Ingram was an undergraduate student here at Santa Barbara that worked with me, and Eleni and Sophia and Doris Theodoro and Christos Manakis are colleagues of Eleni when she was a graduate student at the National Technical University in Athens. Laura Zerbel was a student of mine. Martin Kroger was a supervisor with Eleni in Zurich, I believe. Kyle Chapman, again, a student of mine with whom we worked here in Santa Barbara. And Paul Asperger, the last, is a colleague of mine, and Eleni and Paul and I worked on a project together, which I'll discuss toward the end of things. So that's, and I'm apologize for anybody I've forgotten. I think these are the people whose names came up as I was going through these slides. The story sort of starts quite a while ago now with the folks in the era in the 1970s. I mentioned here Paul Flory, who made, how to say it, this work with polymers and polymer gels accessible to mathematical people by proposing models that involve random walks in three-dimensional space, and observing that they were able to characterize the behavior of polymers under certain temperature or solvent conditions. The random walk, of course, is just a unit length step in a random direction, a sequence of those, thereby describing a sort of polygon or an arc, a polygonal arc in three space, and the collection of those then would characterize the sort of spatial properties of these polymers under conditions where there were no real interactions between with the parts of the chain, but included the fact that chains could not self-intersect. So there was an excluded volume that prevented these chains from intersecting each other. So I just gave you a picture here. Also, Paul Flory, a colleague of ours in California from Stanford, of a random walk of length 100, and you observe that the structure is really not all that homogeneous. It really has some really special spatial characteristics which were able to be predicted mathematically using sort of the geometric methods, statistical methods, and so on. A bit later, Sam Edwards, or Sir Sam Edwards, who is at the Cavendish Laboratory in Cambridge, England, got interested in these matters at some point and proposed or asked questions about the influence of the topology, the spatial characteristics of these arcs or closed chains, and try to include the topological constraints in the study of statistical mechanics in 1960 or late 1960s, early 1970s. And his papers were, for me, one of those catalytic kind of experiences that got me thinking about the relationship because, of course, I was interested in knots and various kinds of entanglements and so on in space, at that roughly that same period. A little bit later, actually, not at a contemporary of his, but rather more toward the 1980s. Similarly, I forgot. I was going to say there was, of course, a rather famous conjecture that that as a random walk got longer, the probability that a knot would occur should asymptotically approach 1. And so we have DeWitt, one of DeWitt's students, Van Diao and Nick Pippinger and Stu Whittington, all discovered in the late 80s, proved in the late 80s that, in fact, this was the case. And so roughly at that time, and I think stimulated by a workshop that occurred at Santa Barbara, I actively got involved in trying to understand these things and did some numerical simulations of random equilateral polygons and determined the knot type. So this would be roughly following the creation of these Humphrey polynomials and other Jones polynomial and so on. And one can see rather strikingly that, in fact, this is the case, and it grows really quite rapidly with the length, or the length scale of the polygon. So after a number of years at Santa Barbara, where I was involved in university kinds of projects, chair of our faculty, chairing the long-range development plan, the university gave me an exceptionally about a 1.5 or 2 year leave of absence during which I could do anything I wanted. And what I decided to do was to go to France and to learn about how to apply topology to the study of polymers. And one of the people there that influenced a lot of my early thinking and introduced me to the work of Sam Edwards and Flory and others was Pierre-Gilles de Gennes, who was at the Collège de France at that time. And his contribution to this study was to notice that a polymer chain in a gel, of course, could move, and it would sort of take up a space which he described as a tube, like a tubular neighborhood or a sort of fat tube. And the study, the spatial relationship of these tubes then would have a great influence on the gel, properties of the gel, properties of the material, and so on. So the key point here is that, yes? Oh, okay, I just heard a voice, got me distracted from my notes. So the key idea here is to be able to kind of characterize the spatial properties that these would enjoy and how they would move and so on. So that was sort of the focus of my, I know exactly when the period was. It would be the 1984 period because I got diverted by the Jones polynomial at that time, and so didn't really pursue that. But that's another story. The key thing today is that topologists already understood how to try to study the motion, the properties of these of closed circular polymers, or even from the work of DeWitt and others, the relationship of arcs. We understood from the 1930s how these polygonal models could move. Kurt Reidemeister, who is a picture there on the left, proposed or described this for us using sort of movements of polygons, which maybe we would call piecewise linear topology, by observing that if there was I wonder if I can sort of if someone see a little mouse here, there's a triangle here in which nothing else enters this triangular region. And so you can collapse the triangle down to the dotted segment there. So this kind of triangle move, along with breaking up your polygon into smaller pieces, subdividing it, we would say, or amalgamating, those movements were all that was required to describe any possible movement, piecewise linear movement of a polygon. Okay, so they gave rise to, as maybe I'll have a slide later showing the famous Reidemeister moves. The three triangle moves come from just studying the consequences of projecting these triangle moves onto a plane. But in the polymer world, these ideas were, I think, maybe rediscovered. I don't know, in fact, whether they were aware of Kurt Reidemeister's work from the 30s. But in polymer physics and in biology, these kinds of moves were employed to try to simplify the structure by trying to form what we would call, let me see, I keep remembering and forgetting sort of principal paths or something like that, shortening the curves, but keeping the endpoints fixed until they, as you see in the middle slide there, they sort of hang up on each other, right? They get stuck and they can't move any further. They're sort of straight segments and then little bends and more straight segments and bends. So those kinds of obstructions then, pardon me a moment, I don't know, I have a picture, I have people's pictures here obscuring my picture, lead to a way to try to understand the complexity of the polymer system that you're looking at. So on the right-hand side, you see a picture of a cube in which the whole structure has been simplified. And these cubes are the sorts of things that arise when you look at the periodic boundary condition models that we'll study. So here, when you have closed things, of course, you can have trefoil knots, you can have Borromean rings I show because they're quite pretty, quite wonderful. But collections of rings in space that you can try to apply topological invariance, knot theory, linking, and so on. And that's, in fact, what many of us have been doing for quite some time. So, pardon me while I'm trying to get myself organized. So today, I'm not going to talk about one aspect of that, namely the applications to biology and to the knots that are present in studies of DNA or proteins. There have already been, I see, a couple of lectures by Sophie Jackson and Joanna Sulkowska who have described a lot of this work already. I'm going to focus merely or principally on the polymer side of things. And the periodic boundary condition part plays a principal role in this. Okay, so when you want to have, sort of coming from statistical mechanics, you want to have a system where you can describe in a finite way the structure of these materials, and you do not want to have boundary conditions. You don't want to have boundary effects. So one does this by taking a model, as you see in the center screen. We have some open arcs there, or on the right-hand side, closed chains. And then you translate these, in this case, in 2 dimensions, in the 2-dimensional plane, using a lattice of translations to fill out the entire plane, creating an infinite system. So this is a sort of a periodic boundary condition model. You can have a 1-dimensional long sort of strip, 2-dimensional or 3-dimensional kind of system. And it's this kind of a structure that we'll want to study. The images here are those that were created by Eleni Panayiotou in her research, and I think I've taken these either from our papers or her thesis or other things that that she has been implicated in. So, as I said, you can have three-dimensional cubes, sort of two-dimensional tiles, or one-dimensional segments there on the right, where you translate these just along a single directional axis and create a kind of one-dimensional system of entangled structures, even though we're working in a two-dimensional context. So in the middle, I think of it as sort of a laminar kind of thing, and on the right, sort of a tubular kind of structure. So the question is, then how do you determine the characteristics of the linking entanglement present in such a gel? Okay. Well, how did the material scientists, how did the polymer physicists do this? They did, as I mentioned earlier then, try to simplify the structure by applying these triangle moves until it was sort of rigid. You could not simplify it any further. And then they looked at the characteristics of the structure that you had. So in this, on the right-hand side, you'll see a structure with a couple of white squares where you see these little kinks or bends, and they call those entanglements. And so one could count the number of entanglements and work with the density of entanglements and try to then associate those to the structures. Right. So on the left here, I've just added the pictures of the triangle moves that are associated with the Reidemeister moves, and those are the kinds of things that you would employ in space. One thing I should say about this, the way in which this was accomplished was to sort of randomly go through your structure and look for triangles that could be simplified. And it was that feature that really caused me to be interested in this whole subject when it was applied to proteins, because we realized that if you do one sequence of moves, you'll get one structure. If you do a different sequence of moves, you'll get a different structure. And so there's a question about how the things that you discern in that structure depend upon the sequence of moves. And so I proposed or realized this was really problematic, and that if you did one thing in one way, you might end up with a trefoil knot, and another way an unknot. And so that would seem to be quite worrisome. A different story, however. So you could apply this this method to polyethylene, and in fact, this is what Eleni and I and Sophia did in collaboration or in consultation with her colleagues there in Athens. And the question was, well, is there topological information, is there linking information lost in the application of this algorithm, in this Kreta algorithm? Roughly at the same time, Martin Kroger had an algorithm very similar to this that called the Z or the Z1 algorithm, and he applied the same methods to get, or similar methods to get, a kind of related structure that I've shown here. What information is lost when you do that? How does this depend upon the sequence of, applications that you do? That was really the question. And okay, and so end of first step. So that was the world sort of before Eleni, and what was being done to understand the nature of entanglement in, let's say, polymeric systems of this character. And I see I've already used up 20 minutes, so maybe time for questions about the context in which we want to be applying or discussing Eleni's thesis work and its applications. I don't know what to do next. DeWitt, you're in charge, I think.
Questions?
Well, it's Renzo here. Hi, Ken.
Hi.
I have a very basic curiosity. You mentioned the relationship with Reidemaster moves in the context of polymer physics. I wonder, are you referring to kind of stick model in practice? I wonder how do you...
Yeah,
I wonder the role of Reidemaster type 1 move. We know that is a twist move, but technically speaking, there is no intrinsic twist in your sticks. Or is
no, it's
any?
not. No, Renzo. Yeah, sorry, pardon me for being enthusiastic here. It's early in the morning in Santa Barbara. It's not a twist move, you see. It's really a triangle move, and I will go back and show you on this slide, if I can move it, at the top or in the middle of the page. So the Reidemeister 1 move, of course, we think of it as a twist move, right? Because that's what it looks like in other contexts. But in fact, as it arises in Reidemeister's work, it is a triangle move.
Right. That is interesting. Yeah.
Yeah. Okay.
Thank you.
Sure.
Okay, Ken, take it away.
Okay. Let me try. Coffee break. Okay. Onward. Right. Okay. So here is Eleni, who we all know, and I have to move the little pictures of you folks out of the screen. Here's Eleni, and only a few years ago. And so, in my mind, she started in this endeavor wanting to look at linking between chains, let's say linear chains, and so the idea that she pursued already in her master's thesis, as I recall. I should know about this because I was one of her supervisors. So in my memory, it was in her master's thesis. She applied the Gauss linking number formula that's shown below here to open arcs. And so as you see above, there are two sort of open half circles which look like they're entangled. For Gauss, with closed curves, of course, we know that the linking number is an integer, but you can apply this formula, this method, to give a real number characterizing the extent of linking between two oriented arcs simply by doing this integral. And so you get a real number, a linking number between any two oriented arcs. Now, so the Gauss linking number gives you an integral, as shown in at the top, but if you break it just a little bit at these two ends, you can get something which isn't quite 1, but is pretty close to 1, because the gaps here are quite small. And as those gaps get smaller and smaller, that number actually converges to 1. And so this integral is very, very nice because it depends continuously on the geometry of the associated arcs. Also, and I think to point out that will be very critical to further applications is that this can be done by computing sums of the linking number between one arc and the linking number of another arc. Okay, so here we've got 4 arcs, and so there are 16 pairs, and so you can have 16 calculations, add them all up, and that's what you get. So it's important then that arcs can link, and as shown below here, the linking number on the left is about about 1600ths, where on the right it's about 300ths, and the difference is, of course, the separation between the arcs. So that's another aspect of this that will be important later. And again, I should remind you that I'm using slides that I've gotten from Eleni rather than ones that I've created here myself, coming from either some lecture that either she or I gave about these matters. Okay, so it's a linear process in the polygonal world, and it depends upon the character of these straight line arcs, how close they are, and what their orientation is. For example, if these arcs are planar, there's no linking. It's only when they're not planar that you actually, this linking integral will give you a non-zero number. Another observation here. So then back to the sense of application there, where you're wanting to apply this in the situation of a periodic boundary model. So you see here then a square kind of rectangular cell with a blue arc and a red arc here, either on the right or the left. And then the structure says, well, translate the cell according to integer translations, both left and right, to create for yourself an infinite system. What makes it a periodic boundary condition is that what happens on the left-hand side of the cell is exactly what happens on the right-hand side, so that you can juxtapose the two cells and create a structure there that makes sense, okay? And so you can continue and make this chain forever. Now, Eleni's idea is what we would call the periodic linking number. So imagine you look at the blue curve in the middle there, and you want to calculate, let's say, well, in this case, it's linking with the red curve. Okay, so what she proposes to define is that this periodic linking number is going to be the linking number of the blue cell with all of the translates of the red cell. So in the formula, the summation is over the translations, and the J naught might be the red one, and then you translate that according to your integers. So you add all those up. Well, for closed chains, you say, what's the deal here? Because closed chains are compact. And so the blue one can only extend through some finite number of those linear cells, and then anything that's beyond there won't link with it, because we know the Gauss linking number for two separated things is going to be 0. So that, in effect, for the picture that we see here, it's actually just a finite sum. And in this particular case, not very big, of course, maybe 2 or 3 terms. Anyway, so that's the idea, to add up the translates, to take one cell and then translate any other cell throughout the whole periodic system and calculate the linking numbers between them and add them up. Okay, so that's the key idea, at least one of the key ideas. For other reasons, I just want to remind you that there is a notion that is derived from a sort of Gauss-like formula where you have a self-linking number. And the self-linking number then is really a writhe term, that's the left-hand integral, plus a torsion term, which is the right-hand integral, the self-linking number. And so Delaney defines the periodic self-linking number of an arc or of a chain to be the self-linking number of that chain plus the linking number of that chain with all of its translates. Okay, and that will give you a sort of how a chain links with itself, both sort of the physically thing, but then because of the periodic boundary conditions, it may be that a translate of that chain will link itself again. So you add all of those up. So now we have a self-linking number and then a linking number for these chains. And so that provides a very attractive kind of structure for analysis, namely a linking matrix for a system in a periodic boundary condition model, where the matrix, the diagonal terms are the self-linking numbers, and the off-diagonal terms are the linking numbers. And then you can apply, of course, all of the kind of standard linear algebra devices that are appropriate for symmetric matrices, symmetric real matrices. And so at some point, perhaps I'll talk more about that. Okay. So these notions apply where the chains are closed, as we see on the left, in which I've mentioned that one actually ends up with a finite kind of summation. And in the middle, where we've broken them, now you have an infinite sum. Here, it's a doubly infinite sum, right? It's indexed both horizontally and vertically. And so that's a doubly indexed sum. And if you're in three dimensions, you're going to have a triply indexed sum, because you're going to be adding in the x direction, as it were, the y direction, and the z direction. So you have a triply indexed infinite sum to deal with. And for infinite chains, that's where there's no compactness. You get an even more challenging infinite sum under these translations. And so, of course, this is all really wonderful, and we have some wonderful definitions here, but and they seem to have some wonderful properties. I hope that's the next slide. Yes, they do. So the linking number is symmetric. I've hidden. It really captures the global structure of a gel with all of these chains. And one of the theorems that Laney proves is that if you choose a chain or any translate of it and apply the definition, you get the same amount, same structure, because of the homogeneity of the system. Okay, so that's of course really quite wonderful. But one of the sort of stories from graduate school is, okay, we've developed this wonderful theory, and you're about to defend your thesis, and somebody asks you, how do you know this thing exists? You're talking about a type of manifold or a function, and one of the horror stories that graduate students tell each other is, well, what? Maybe someone will ask you a question, and you'll realize you're talking about the empty set. Well, here we're talking about infinite sums. So how do we know they exist? Exist, of course, means that these summations need to converge, right? So that is the principal content of Eleni's thesis, that in fact, these things actually exist so that you can actually use them. And so her 2012 thesis has like three major pieces to it. It's sort of a warm-up. So the first one is, what do you do when you have a singly infinite sum, right? And so you have to prove that this sequence converges. She proves it converges uniformly and is bounded, and she gives a bound for it. How big the linking number can be in terms of characteristics of the geometry of your periodic boundary condition system. And so I'm going to have some slides where I say a little bit about the proof, very little about the proof, actually. But the point here is that this system converges more or less, in my mind at least, like the summation 1 over n squared as n goes from 0 to 1 to infinity. So it's a 1 over n squared kind of convergence. Well, all right, so that's, you build up your optimism here, and you move on to 2 dimensions. And so in 2 dimensions, now you have a much more challenging task, because you've got a doubly indexed infinite sum, and so you have to be able to control this much more strongly, and you have to be able to organize your summation in a way that allows you to exploit the control of the size. So one of the key things here is the fact that, in fact, you only need to worry about single edges, because any chain is going to be consisting of a finite collection of single edges. So you need to worry about how those edges, if you have two arcs in space, you hold one fixed, you take the other and you translate according into your integer lattice, now two-dimensional. How do those contributions accumulate? Well, here in 2 dimensions, you can exploit a bit of a mirror kind of reflection through the origin or through the center of this, and you get a kind of cancellation as things move farther and farther away that you can estimate. The challenge then is you need to, I don't know if you see, I'm waving my hands in the air. I don't know if you're seeing this, but anyway, I'm saying that as you move out away from the origin, that is a kind of summation you can control if you can estimate what happens on a circle of some radius. So this is her sort of, how to say it, her magic. She's able to not only estimate as things are separated how much your contribution is, but the number of terms that will occur in cells at a particular radius from the center. And so you do an estimate that controls those things, and it turns out with this sort of cancellation thing in the number of cells around a sort of circular radius, you can get convergence. Okay. And so the result is an estimate that looks like that, which is, at least for some of us who are top topologists, somewhat terrifying. But Eleni manages to do analysis and even more, as we'll see in her third theorem. Oops. Right. 3 periodic boundary conditions. All right. The argument that she employed in 2 dimensions is not strong enough to give her the result in 3 dimensions. And in 3 dimensions, you need to be able to now exploit spheres at a certain radius, count the number of cells that occur in sphere along the edge of a boundary of a sphere of a certain radius, and the size of all of those contributions. Let's see here. I should check my notes here someplace here. Right. Well, so the principal components in that argument is that the number of cells of a certain radius, a certain size, sort of grows like the square root of n times the log of n squared in 3 dimensions, whereas in 2 dimensions, it turns out that it's like n to the 7/22 power. Now, where do these numbers come from? Well, of course, number theory. And so this turns out to be some really, I'd say, hardcore number theory, and some results that let's see, did I write down some years here someplace? Are really quite recent. No, I don't think I wrote down the numbers. But in any case, so you have to do that. You have to be able to make those estimates, and then one of her brilliant, insights is that she can apply this for a very special subclass or a special subclass of structures, and then by using analysis show that you get convergence for all of them. So it's a mixture here of topology, geometry, number theory, and analysis that leads to this estimate that we see here in this proof, that you actually get convergence. So that's what I've laid out here on slides, which I think are going to be available. And there's a reference to the publication of her thesis in the Journal of Computational Physics. You can see that it's about 40 pages of argument, and that is a concise version of the argument. This is not the full elaborated version. This leaves a bit of effort to the reader. So she makes these estimates, and that's what they look like, and that's about, I've said as much as I really want to say about these things. So, okay. So brilliant. We're celebrating, okay, these things exist. And then we have a tool that we could use, we being Eleni and maybe in collaboration with others, the et al. I think the et al. Actually is the Athens team, and with me as a sort of exterior person. Apply these to the polyethylene gel characterizations there of Theodorus and Zovanakis. And so what one sees is that as you do these Kreta simplifications or Z1 simplifications, you don't really lose much of the topological entanglement. That these simplifications actually preserve these, and you're able to use the linking number if you wish, or to characterize the kind of entanglement within the structure. Excuse me while I look at the time here. Okay. All righty. So, what more? Just a quick comment here. Namely, you can also now apply the periodic linking matrix and study things like the eigenvalues of the Laplacian of the associated weighted graph. You can associate a weighted graph to this because it's a real symmetric matrix. So it's like an adjacency matrix, but with weights on them. The Cheeger constant is a inequality, a number that comes from sort of Riemannian geometry, the study of manifolds, and it's a measure of how the extent to which there exists pinching, like a dumbbell, like two big balls separated by a little narrow neck between them. It identifies the existence of these narrow necks, then has been extended by Fanchu Young, I think, or Fan, actually, to graphs, spectral theory of graphs. And so there's a Cheeger constant for these kinds of graphs that then can identify the extent to which there are concentrations of globular locations of linking centers in these structures. So the Cheeger constant identifies the cases where there would be little linking and there'd be sort of blobs of structure separated. So that's the application then of the linear algebra theory. Right, so we applied this to these kinds of gels and looked at the asphericity. The asphericity is really a measure of the average or the characteristics of the eigenvalues of the structure. And as I mentioned, then the Cheeger constant helps to identify sort of constrictions. Okay, and so we applied that in several models, as indicated here, where we have looked at structures with different densities, with different lengths, and so on. So, time for hopefully, a few more questions, and then I can try to sort of close things off with some newer applications.
Any questions?
It's Matt Bright here from the University of Liverpool. I'm sort of interested in looking at this sort of approach to look at things like entangled crystal networks, and whether that would be possible. I suppose one of the first practical questions is in terms of calculating this for what is presumably very large networks. Is that do you use kind of just very powerful computation and is it a lengthy process, or is there a way to kind of automate the calculation of it, to simplify the calculation of? Yeah.
Excellent question. Excellent question. One of the blessings of this kind of situation of the polymer gels and the periodic boundary conditions is a kind of decay rate as you get further and further from a particular chain that you're looking at. And
okay.
so you can look, part of Eleni's research indicated that you could get, let me just make up a number, like we all do, like 90% of the structure by only going out a short distance, you see.
Right.
So she made estimates which then said, okay, for numerical work, we could get sufficient accuracy by taking some very specific finite number of terms and then terminating our estimate at that point. In a graph situation, it depends then on the characteristics of the graph, and in terms of weighted graphs, of course, that's what we're exploiting here, right? That we have sort of the linking number terms for things that are like far away, could be very small.
Right. Thank you.
Mm-hmm.
Question. In Lange's definition of linking number, which is the real number, I would take it that reparameterization does not change the value of the integral. Is that correct?
Yes, that's correct. Right.
Uh-huh.
Yeah, that's the blessing of the Gauss linking formula. And I should say two things there. It doesn't depend on the parameterization. And one of my tests for students who wanted to work with me was to give them a paper written by Tom Bancroft in the maybe 60s or something, in which he gave a combinatorial formula. He gave a formula for computing the linking number of polygonal curves. It's a rather challenging paper because, of course, he left a lot to the reader, but that reduces so Eleni from that paper wrote a program, an algorithm that quickly calculated linking numbers between polygonal curves. And so that made the calculations fast.
I would very much like that reference if it's available.
The Bancroft reference?
Yeah, that would be Banshaw, is it? Okay.
So I would simply, I imagine I have this on my laptop, and if you could send me an email at Millett, Millett @math.ucsb.edu, I could probably send you a PDF.
Okay. Thank you very much.
You're welcome.
Can I ask a related question? Keith Moffat here.
Yes.
They're related to the self-linking number, something that Renzo and I worked on.
Right.
It's an invariant as long as you don't distort the curve through what we call an inflectional configuration, because then there's a switch between the torsion term that you indicated and the internal twist if it's a tube. Now, you're not dealing with tubes of finite cross-section. As I understand it, you're dealing with simple segments. And so you can't include somehow this tube structure effect. And I wonder how you get around that. Maybe you just avoid distortions through inflection points.
Keith, wonderful question. And I would have to apologize to everybody if I inadvertently used the word invariant in this context. Either that or for my work with knots of open arcs. They are not invariants, as we know. And so I'm really looking at, and I think we're looking at here, the sort of frozen structures. There's no dynamics involved. No dynamics yet involved in this. So I'm not allowing for any kinds of deformations that would be important and would be part of the work that you're describing. They're all really just fixed in space, frozen in time and space.
Okay, thank you.
Thank you.
Another whimsical question. Even though the definition involves derivatives of gamma at certain points, I cannot avoid asking myself the question, can one give a definition which does not involve derivatives, in other words, which applies to parametrizations which are not necessarily differentiable?
Right.
I don't know if this makes sense or not.
So yes, absolutely. And that's the point of the remark about the Banchoff paper, which gives the definition of these, or the way to calculate these quantities for polygonal arcs.
Okay. Thank you.
You're welcome. Yeah, therefore, how to say it, for public relations purposes, it's wonderful to use Gauss's formulas and the formulas that work for smooth curves with non-vanishing derivatives and so on. But the reality is, we basically build off standing on the shoulders of Banchoff's formulas and methods that apply to lots of other interesting things in topology, but derived from that original paper of his. Okay, shall I move on? Let's see here. I have 8 minutes or so. Who knows? So back in the 80s, Dejean proposed a study of what he called Olympic polymers. And these are polymers composed of collections of closed rings, like the Olympic rings. And so, of course, these structures lend themselves to study using periodic boundary conditions as well. And so, if I remember right, we were inspired by a paper by Javier Azuaga and friends about this kind of chenoplast, where you see on the left, it's a kind of I get in trouble here because there's like bacteria and virus. It's a parasite that causes sleeping sickness and has a collection of lots of little circles and then a few big circles. And so how this all occurs has been of interest to people because of the disease dimension of all this for quite a while. And so there are some images here. I got one from a paper that I've cited from 2004. But this was known quite a ways back, and how this occurs and what are the characteristics of the structure, that's what caught my attention. And then I learned later that Dejean was interested in these things in the 1980s as well. And so we proposed, we being me, we had a student, and Eleni had a student in Santa Barbara named Spencer Ingram who wanted an undergraduate research project, and we said, well, let's look at that. Let's look at a collection of circles under three-dimensional periodic boundary conditions and varying densities, and look at the nature of the entanglement there using our linking numbers kind of structure. And so this is a one-slide kind of version of this, where we have density along the bottom axis and then probability of occurrence vertically. And this was not the world's most sophisticated model, first of all. I think if we were to continue in this direction, there are some things that we would do differently, and others have gone on. Arzuaga and Vasquez and friends have gone on to do more in this direction. But one thing we noticed was this sort of question of what was called percolation. Namely, in these kinds of systems, it was observed that in an analogous systems, there was a point of a density where suddenly things went from totally unlinked and unentangled to total global entanglement in all dimensions. And so what Spencer noticed in our data is that looking at this carefully, we could discover that because of the character of our system, there was a point at which a kind of one-dimensional structure occurred, where you might think of this sort of system of rings being actually now sort of, if you hung them together, like a whole bunch of spaghetti, just laid end to end, right, filling up space. They had a one-dimensional kind of structure, but they're all separated. And as the density increased a little bit more, you would get a kind of laminar kind of structure there, where you've got like sheets of lasagna and you're laying those next to each other. And then finally, then the whole system being entangled. So that's one of the sort of applications of Eleni's work and her way of looking at things that led us to recognize the fact that in at least the models we were looking at, this was a rather surprising kind of observation. We expected to see what the folks who were looking at percolation would see. And so this was a rather exceptionally surprising part of this. The next thing, and the last thing I want to talk about today, maybe almost the last thing, has to do with an application where we're looking at the mechanical properties, again, of a periodic boundary condition. And here we're now looking at dynamics. So where some time scales involved, right? Where if you let it maybe look more liquid-like after a long scale. This is work with Eleni and Paul Atzberger and myself, where we have a variety of kind of structures. I've given you some pictures of that I got from Eleni about different kinds of ways in which linear strings or strands can be woven together. Okay, and so here are the ones we're going to look at. On the left, you see a line change, like these spaghetti things. But then in the second one over, you have them going in ways which are parallel to the X, Y, and Z axes. So they're sort of like a jungle gym kind of thing. And then the third one is a more dense version of that. And then the final one, way to the right, is where we've woven them along the lines of the picture I just showed you above, where you've taken sort of a basket thing and wove them in and out in these three-dimensional properties. Now, what we're proposing to do with these things is to move them, to exert a force on them, a shear force, an oscillating shear force, in fact, and then study the dynamics of the whole system under a sort of molecular dynamics modeling and see what are the characteristics that evolve or that come out of their behavior under this periodic oscillating shear force. So here's just a picture of the quantities of the properties of different densities, and then the shear force is given by this kind of picture with the blue square, with the square sort of moved to the right here a little bit by this periodic force, using what I'm told are called the Lee-Edwards boundary conditions. And then we're going to look at their dynamics using this Irving-Kirkwood method and I wonder if I wrote it down. It's like a molecular simulation program. The LAMPS model, I think it's called. Anyway, moving ahead quickly then, this is what happens with after some amount of time. The ones which are looking like the spaghetti, you can see a little wavy thing going on. If they're tied together sort of infinitely, right? If you have a bound on them, they start clumping up a little bit here on the right-hand side. Similarly, for a more dense situation, now you see this periodicity of the cell in a really strongly amalgamated kind of system under the open chain. Oop. Hmm. And so these are the more dense ones, and then the woven one is the W3, where you see how the topology really has a really profound effect on the on the sort of steady state characteristics of the system. So there is a way of characterizing this that involves studying at the bottom. You'll see this equation with a G2 and a G1. The G2 term sort of captures the characteristics when that's the dominant one, it looks more like a liquid, whereas the G1 term, if that's the dominant term, it looks more like a solid. Things are really tangled together. So this is the graph of the data that we had out of this study. And I should say, a study of this sort, the amount of effort that of a study of this sort uses a quantity I learned about producing the kinds of pictures of DNA. Namely, the time length is measured in postdoc years to create to get all of this working correctly. Namely, Eleni spent a long time and a lot of heroic effort in order to produce these graphs. And so thanks to her, we have kinds of things that can characterize, and we can see how they characterize the various structures and how they behave with the sort of different growth rates that come from the statistical mechanics of polymer physics. Okay, so this is just the key things are these exponents, the half and a quarter and the 3/4 and 3/2. I'm moving ahead here because I'm running out of time, but also this loss tangent is a key parameter here, where you see how it depends on the frequency. The frequency is measured here in the bottom. So I have, thanks to Eleni, this is what I'm looking for, tells you very much how this is a measure of the rise, the absolute rise, how the characteristics of the systems are manifested in this kind of entanglement. With at the lower left, this is the woven one. The W3 is the one that's woven. And then as we move sort of up to the upper right, we have more and more freedom, more and more, how to say it, more and more behaving like it's kind of a liquid versus a solid. And here's another one. This is with the linking, now measured by the linking. So at the very highest linking, then is at the upper left, and as we get more and more liquid-like, then you see lower and lower linking. And so we now have, because of this paper with Paul Etzberger, Eleni now has the quantitative ways of characterizing the behavior of a system under dynamics, under this shear kind of force. And then I remember once at a wonderful meeting in honor of Keith, we talked a bit about what happens in one-dimensional systems. What a memorable meeting that was in your honor. It was a great fun. And so that's a kind of one-dimensional tubular system that we've encountered. And then there is the sort of two-dimensional laminar system that we encountered with Spencer, both of those, that where we can apply these kinds of linking. Here, we did a study where we had planes of a two-dimensional system, but we stacked them, like as occurred on the left. This is something I took at our local building materials shop, I think, a while ago, looking for something that had a laminar structure. Oops. And I should have a graph here, just a second while I look, but I don't, because I'm going to tell you something else. So anyway, what happens is, as these are separated, you get a kind of independence, and as you start move them next to each other so that the laminar structures start to how to say it, start to intersect, then you get a very different kind of sort of linking kind of entanglement structure that you can study using Eleni's methods. Okay. One final thing, concluding comment. This is just publicity, okay? My way of saying thanks to Eleni. This is a paper that Eleni and Luke Hoffman put on the archive about knot polynomials for open and closed curves. In my mind, this is sort of in the spirit of my ongoing work about knots of knotting in open arcs. And so I was really inspired by this, and I've given you the reference at the bottom so you too can look at it. But what I am now able to do, inspired by her work, is tell you that the average Homfley PT polynomial of an open trefoil is given above. Now, for those who know about Homfley polynomials, this term, this 0.36 term, is the term that comes from the unknot, which has polynomial 1, and the other terms come from the trefoil knot, which has terms -2, -1, -1. So now I can with my program estimate the average Homfley polynomial of a spatial curve. What Eleni and Lou propose and can do is tell you the average Jones polynomial of an open curve, and they're exploiting their ability to do this for knotoids and then integrate over all possible knotoids by directions of projection to a plane and so on. But anyway, the purpose here is to say thank you to Eleni for sharing her slides, and here is a paper, her most recent paper that I know of anyway, on the archive. So thank you very much.
Thank you, Ken. That was a terrific talk. So questions? So Ken, I've got one. Speaking of tubes, as Keith was speaking of, one of the important, that's not a bird.
Not your garden.
One of the important things about tubes is that for DNA, you've got link equals twist plus ride. Is there anything like that in these periodic linking numbers that you could get to? Sort of something along those same lines?
Well, yeah, I think DeWitt. So first of all, these are of course just they're for the DNA thing. You have a framing, right?
Yes.
And that's what gives you the twist plus rise.
Right.
Here, to the extent that there's a connection, that would probably be in the self-linking number, where you have the rise and the torsion, right?
Right.
And now, it doesn't, at least to my knowledge, doesn't play the same kind of role here as it does there, at least to my experience and knowledge. Maybe someone else knows more about that, but that would be the connection. This is all just simply, excluded volume, curve, but no framing.
Right. Yeah, you'd have to have ribbons or something like that to do that. So.
Right. So this would be a question for Eleni, actually, because there are, of course, colored Jones polynomials that have to do with framing, and I don't know whether there may be kinds of framing things that come from knotoids, but this is a little bit beyond my expertise.
Okay.
I have a question to Ken. Ken, do you have any plan to consider spherical volumes?
Pardon my laughing.
Maybe not.
So the answer is yes. And then I'm reminded of my Native American traditions that we always answer a question with a story. And the story is this was the first, inspired by this conference, this NATO conference, then my acquisition of a Macintosh and Mathematica, I was able to numerically determine the probability of linking of two triangles inside of a ball. I woke my son up at 3 o'clock in the morning and asked him if he knew what the answer was, and his guess was very close. But in fact, yes, the answer is yes, both within balls and within cubes. And then there was another time where just to get a upper bound on the worst possible case, I said, take the uniform distribution of points in a unit cube as your probability distribution, select a random chain from that distribution and calculate the probability of knotting. And so one of my first applications to try to see how bad knotting could be, inspired by DeWitt and Stu and Nick and others. And many of our colleagues have too. Christian, I think, and